Hey everyone, welcome back. If you're gearing up for the Nutanix NCP-MCI 7.5 certification, you are the exact right place. Today's explainer is completely dedicated to Objective 7.1, Containers and Replication Factor. Now, for us infrastructure admins, this isn't just exam trivia, it's the absolute bedrock of Acropolis Operating System, or AOS, storage. We're going to take a really methodical, peer-to-peer approach here. My goal is to help you thoroughly master this so you can spot the correct answers a mile away on exam day. Plus, it's just critical for understanding exactly how your cluster protects your organization's most valuable asset, your data.
So, here is our roadmap for this explainer. We'll start with why containers matter, then walk through RF2 with some really specific examples, expose a few nasty exam traps, and wrap up with the non-negotiable fact you just have to memorize. Let's dive in.
All right, part one, why containers matter. Honestly, if you understand the underlying why of this architecture, memorizing the what for the test becomes a total breeze.
In AOS, a storage container is not just, a glorified logical folder. Far from it. It is the fundamental unit where you configure your data reduction and data resiliency. When we talk about reduction, we mean compression and deduplication, the stuff that shrinks your app footprint and saves you serious cash on storage. And resiliency? That's the strict rulebook for how your cluster survives hardware failures. Think of the storage container as the absolute core boundary for all of these settings. When you're designing your storage, the container is where you're making your biggest architectural commitments. It dictates how your data behaves, how it shrinks, and most importantly, how it survives.
Think about what this actually looks like out in the field when you're managing Prism Central. When you pop open a storage container's settings, it all clicks. You've got your replication factor right there at the top. And right below it, you've got your toggles for compression, cache, and capacity deduplication in erasure coding. By anchoring these concepts to what you actually do in the UI every day, it'll be so much easier to remember on the exam that all these massive optimization policies live securely in one place, at the container level.
Moving right along to part two, we're going to deconstruct replication by looking at two highly specific cluster scenarios. Before we get into the weeds, let's just baseline real quick. Replication factor, or RF, is exactly what it sounds like. It's the precise number of data copies maintained by the cluster to ensure fault tolerance. If a drive fries or a whole node suddenly drops offline, your cluster seamlessly relies on these copies. For the end user, it's completely invisible. They don't notice a thing. The system absorbs the hit and just keeps serving data.
Okay, so let's walk through a standard RF2 write operation. Step 1. Your guest VM writes some data. In RF2, AOS ensures two complete copies of that user data are distributed across two totally distinct nodes. If node A goes up in smoke, node B has the exact same blocks. But, and this is a massive shift in how the system thinks, step 2 is all about the metadata. For standard RF2, your metadata isn't RF2. It's actually written with a replication factor of 4, and it is strictly placed on your solid-state drives. So 2 copies for user data across the nodes, but a mandatory 4 copies for metadata locked onto the fastest drives you have.
You might be wondering, why the mismatch? Why go all out with RF4 on SSDs for metadata when the actual user data is just RF2? Well, think about it. Metadata is the literal map of your entire cluster. If you lose the map, you lose the cluster, period. Storing it on the SSD tier guarantees ultra-fast access, which AOS needs instantly for its intelligent tiering to work. And keeping 4 complete copies, that gives you extreme availability, meaning the system can survive multiple hardware failures without ever forgetting where your actual user blocks are parked.
Let's level up to a slightly more complex but super common exam scenario, 1N and 1D. You will definitely see this acronym. It stands for one node and one disk fault tolerance. It's a highly robust setup designed to survive the simultaneous failure of an entire node plus a completely separate disk failure on one of the surviving nodes. It's absolutely critical for enterprise environments where downtime just isn't an option, even during a really bad day in the data center.
Now, to pull off that 1N1D magic, the cluster normally hums along at replication factor 3. But here's where AOS gets really clever. Let's say it's Friday night, you're doing routine patching, and a node goes down for a reboot. The cluster enters a degraded state and temporarily drops the container's replication factor down to 2. It essentially says, okay, I'll store just 2 copies right now and mark the writes as complete. This adaptive mechanism ensures your cluster survives the maintenance window, gracefully accepts new writes, and keeps apps online. Once that patch node boots back up, the cluster automatically heals itself, right back to RF3.
All right, ears open for this next part. Section 3 is all about exam traps and edge cases. This is where test takers stumble because exam writers absolutely love testing you on rigid system constraints.
The biggest minefield is the optional replication factor 1 configuration. RF1 literally means one copy. That means zero data resiliency. If the drive holding that data dies, it's gone forever, no coming back. On top of that, deduplication is completely unsupported in an RF1 container. And here's the kicker. It is a strict one-way street. You can't set up an RF1 container and then magically bump it up to RF2 later when you change your mind. It's locked. You also can't enable capacity reservation. It's a highly restricted, high-risk setup, really only meant for disposable scratch workload.
And that brings us to a massive, destructive exam trap. Because RF1 has no safety nets, standard rules just don't apply. We all know and love the recycle bin for saving us from typos, right? Well, if you delete an RF1-enabled vdisk, it bypasses the recycle bin entirely. Boom. It is immediately deleted. There's no undo button. It goes straight to the void. Make sure you commit that specific exception to memory.
Here's another gotcha. Circling back to that 1N and 1D fault tolerance we just talked about, yes, it gives you incredible hardware resiliency, but it comes with harsh trade-offs. If your cluster is set to 1N and 1D, erasure coding, or EC, is strictly not supported, and neither is deduplication. They love this on the exam. You have to make a hard choice between maximum hardware fault tolerance and those sweet capacity optimization savings. You just can't have both in this specific setup.
Also, keep unavailability routing in mind. Let's say your system has strict rack awareness turned on, meaning it really wants to separate data copies across different physical racks. But maybe you're out of space, or multiple nodes are down, and it just can't place the data in the preferred rack. What happens? Does it fail the write and crash the app? No. AOS automatically gracefully degrades its placement. It places those copies on other available nodes within the same fault domain to fundamentally maintain your RF and keep your data safe.
Okay, we're in the home stretch, Section 4, the final review. We've covered the why, the how, and the edge cases. Time to lock in these absolute non-negotiables.
If you take absolutely nothing else away from this explainer, memorize these 4 things for the 7.5 exam. Number 1, the storage container is your ultimate boundary for both data reduction and data resiliency. Number 2, standard RF2 means 2 data copies over 2 nodes, but backed by metadata at RF4 strictly on SSDs. Number 3, RF1 is optional, offers 0 resiliency, and completely bypasses the recycle bin when deleted. And number 4, eraser coding and deduplication are fully unsupported if you're using a 1-node and 1-disk fault tolerance setup.
To wrap this up, I want to leave you with a bit of a puzzle to test your new knowledge. Knowing these strict AOS rules, how would you architect a cluster that demands maximum storage savings, meaning you absolutely need dedup and eraser coding, but you also can't risk losing data if a single node drops? Think about what fault-tolerant settings you'd have to avoid and which container properties you'd apply. Chew on that, keep studying, and I'll see you in the next explainer.